everyone. In previous lectures, in previous discussion, we have gone through alkyl halides, different methods of preparation of alkyl halide from different compounds, their physical properties as well as their chemical properties. So in chemical properties, we have discussed mainly three different types of reaction: a reaction with metals, nucleophilic substitution reactions. There we have discussed different types of mechanisms or different types of pathways, their conditions. Then we have gone through the elimination reactions of alkyl halides. Now, having learned alkyl halides, now in this video lecture we will focus on aryl halides. So coming to the heading aryl halides, aryl halides are those compounds or halogen substituted compounds in which the halogen is directly bonded to an aromatic ring like benzene. Any compound containing aromatic and halogen cannot be aryl halide. For this compound to be aryl halide, this halogen should be directly bonded to the benzene ring. That is what we call as aryl halides. So look at this, we have this. That is aryl group. Now this halogen is bonded to the aryl group. So we say this is aryl halide. But we can also have, look at this. So we have a benzene ring, we also have halogen, but this halogen is not directly bonded to benzene ring. This is bonded to alkyl group. So we say this is alkyl halide with benzene as a substituent. Whereas in the first class, this halogen is directly bonded to the sp2 hybridized carbon atom of benzene ring. So we say this is aryl halide, but this is alkyl halide with halogen, with benzene ring as a substituent to this alkyl group. So we are going to discuss about this aryl halides. So in aryl halides, look at this carbon to which the halogen is attached is sp2 hybridized carbon. So in case of alkyl halide, the halogen was attached to alkyl group and this alkyl group was sp3 hybridized. Now we have this halogen attached to sp2 hybridized, the carbon atom of benzene ring. So this is what we call as aryl halides. So these aryl halides, now coming to general methods of preparation. General methods of preparation of aryl halides. Now, one of the most common method of preparation of aryl halide is from benzene. That is halogenation of benzene. So we have, look at this, benzene. Now this benzene reacts with halogen in presence of catalyst. So reaction of benzene with halogen in presence of catalyst when one of the hydrogen of benzene ring is replaced by halogen, and this gives you aryl halide. So we have this benzene, we have this halogen, reaction in presence of catalyst, and the catalyst in most catalyst is Lewis acid catalyst. So we use Lewis acid as a catalyst. Now, out of this halogen, the reactivity order of halogen, fluorine is most reactive, followed by chlorine, followed by bromine, followed by iodine. So with fluorine, reaction is explosive, that is highly exothermic. With iodine, reaction is very slow and reversible. So whenever we carried out iodination of benzene, reaction being very slow and reversible, reaction is carried out in presence of an oxidizing agent. Presence of an oxidizing agent like HiO3 or nitric acid is used. So the same method that we have discussed in alkyl halides also. During the preparation of alkyl iodides by halogenation of alkane, reaction being very slow and reversible, the reaction was carried out in presence of an oxidizing agent such that this oxidizing agent destroys the reducing agent Hi formed in the reaction, and the equilibrium is shifted in forward direction, increasing the percentage or the quantity of the yield. So look at this, we have this benzene, this reacts with chlorine in presence of Lewis catalyst. Either we can use AlCl3 or we can use FeCl3, or simply we can use iron as a catalyst. So these are all Lewis catalysts. So benzene reacts with this chlorine in presence of Lewis catalyst, when this gives you chlorobenzene plus HCl is released. We take this bromine in presence of this same catalyst AlCl3, FeBr3 or Fe, when we get bromobenzene plus HBr is formed. But if reaction is carried out with iodine in presence of this same catalyst, we have this iodobenzene and Hi is formed. So this reaction is reversible. So if the reaction is carried out in presence of this oxidizing agent, then this reducing agent, this is oxidizing agent, this is reducing agent. So this reducing agent reacts with HiO3 when this is converted into H2O and iodine. So you are removing the product from the equilibrium. So according to Le-Chatelier's principle, equilibrium is shifted in forward direction, and simultaneously we are increasing the concentration of iodine, which is the reactant in this reaction. So both these factors shifts the equilibrium in forward direction. So this is the preparation of halogen substituted benzenes from benzene. Now, one thing that we have to keep in mind is presence of electron releasing groups. Presence of electron releasing groups in benzene ring increases the rate of reaction. So if the benzene ring contains a particular group which shows electron releasing property, then this reaction will be faster. If the benzene ring contains an electron withdrawing group, then the reactivity will decrease. So any group which is electron releasing present on this benzene ring will increase the rate of halogenation reaction. So this is one method by which we can prepare halogen substituted benzene, direct halogenation of benzene. Then the second method of preparation is from benzene diazonium salt. Benzene diazonium salts. This is benzene diazonium salt, benzene NO2 plus benzene diazonium salt. Now this benzene diazonium salt, when reacts with CuCl in presence of HCl, this nitrogen is removed as a nitrogen gas, and in place of this nitrogen Cl comes. So we have chlorine substituted benzene. So the reagent is CuCl in presence of HCl. We have CuBr in presence of HBr. When nitrogen is replaced by bromine. So these two reactions in which the nitrogen of benzene diazonium salt is replaced by Cl or Br is known as Sand-Meyer reaction. So Sand-Meyer reaction is replacement of the nitrogen of benzene diazonium salt with chlorine on reaction with cuprous halide and hydrogen halide. When this reacts with Ki followed by heating, a reaction of benzene diazonium salt with Ki followed by heating, when nitrogen N2 is replaced by I, that is IO2 benzene is formed. When this is heated with HBF4 or simply we say BF4 minus, heating of benzene diazonium salt with BF4 minus, when we get fluorine substituted benzene. So the last reaction, this is known as Balch-Scheinman reaction. So all halogen substitute benzenes can be easily prepared from benzene diazonium salt. This benzene diazonium salt is stable between 0 to 5 degrees centigrade, so at low temperature. But if temperature is above this temperature, this immediately nitrogen gas removes out from the system and diazonium salt does not exist. So for this diazonium salt to be stable, temperature should be low. So this is the methods from which we can prepare aryl halides. Now coming to this, nature of carbon halogen bond of this aryl halides. We have looked at this alkyl halide. This is alkyl halide and this is aryl halide. In case of alkyl halide, the carbon to which halogen is attached is sp3 hybridized. In case of aryl halide, the carbon to which this halogen is bonded is sp2 hybridized. So when we compare the polarization of the CX bond, so the polarization of CX bond is more in case of alkyl halide than in case of aryl halides. So alkyl halides are more polar in nature than that of aryl halides. So the reason being, in case of alkyl halide, carbon is sp3 hybridized, so electronegativity difference is more. When carbon changes from sp3 to sp2, electronegativity of carbon increases, so the electronegativity difference decreases. So this is the reason why the dipole moment of alkyl halide is always greater than that of aryl halides. Now these aryl halides, due to the presence of this benzene ring, these aryl halides are insoluble in water, as we have discussed in earlier class also. In case of water, we have intermolecular hydrogen bonding, which is one of the strongest intramolecular intramolecular attractive force. So in case of water, we have strong intermolecular hydrogen bond. In case of these aryl halides, we have this simple dipole-dipole type interaction. So when these compounds are added to water, the attractive force between water and this compound is weaker. So these energy released during this process cannot overcome the stronger hydrogen bond present between water molecules, and this is the reason why alkyl halides and aryl halides are insoluble in water. Now coming to this chemical properties of this aryl halides. Chemical properties of aryl halides. Now, alkyl halides shows nucleophilic substitution reaction either by SN1 pathway or by SN2 pathway. Now, these aryl halides, the substitution of this halogen by another nucleophile does not take place easily. That is, aryl halides does not show substitution nucleophilic similar to alkyl halides. So alkyl halides easily undergoes nucleophilic substitution reaction, though by different pathways, different mechanisms, but these aryl halides does not show nucleophilic substitution reaction similar to those of alkyl halides. Now we have to explain why these aryl halides does not show substitution reaction. So the reason for this is, first look at this. In case of aryl halides, this is the first reason. Look at this. We have this carbon, this is halogen. So look at this carbon halogen bond. This carbon being sp2 hybridized, more electronegative, bond becomes shorter, so this CH bond becomes stronger. So this CH bond becoming more stronger, tendency to break this CX bond will be less. Second thing, now look at this does not undergo SN2 reaction, because look at this, SN2 reaction requires rear side attack, but if you look at this, the rear side is completely blocked by this ring, so rear side attack cannot take place. Second thing, this does not undergo SN1 reaction. The reason being, in SN1 reaction, after breaking of carbon halogen bond, carbocation has to form, this benzene cation being very unstable, this does not form. So because of this does not undergo SN1 or SN2 reaction. So the first one is CX bond is stronger. Due to this being sp2 hybridized, bond becomes shorter. And this does not undergo SN1 or SN2. No SN1 and no SN2. No SN1 because benzene cation is unstable. So benzene cation being unstable, benzene cation does not form. So this benzene cation does not form. So if this does not form, then the reaction cannot take place via SN1. SN2, this does not undergo SN2 because a rear side attack is prevented by ring. So already rear side we have a ring. So due to the presence of this ring, rear side attack is not possible. Hence this does not undergo SN1. The second reason for this is, so we have looked at this benzene ring. This halogen has got 3 lone pairs of electron. So these lone pair electron halogen is in conjugation with this benzene ring. So this ring in conjugation, this undergoes resonance stabilization. Because of this resonance stabilization, carbon halogen bond becomes double bond in character. Because of this double bond character, bond strength increases to a much higher level, and this cannot be broken easily. So look at this, we have this if you look at this, in one of the resonating structure, carbon halogen bond becomes double bond in nature. This continues this is shifted here, and this pi electron goes to this carbon atom. So we have this structure, and then we have final structure this. So because of this resonance, carbon halogen bond acquires partial double bond character. So again bond strength increases, so tendency for breaking of this CX bond is very less. So carbon halogen bond becomes double bond in character, increasing bond strength further. Hence, so because of this reason, this Aryl halides does not undergo the normal substitution reaction as given by alkyl halides, but these do show substitution reaction under different pathways. So that we have to take up. So first, that is reaction with metals. Reaction with metals. So we have looked at this. This is Aryl halide. These aryl halides react with magnesium in presence of dry ether. So this gives you aryl magnesium halide. This is aryl magnesium halide, which is commonly known as Grignard reagent. So as I told you, magnesium halogen bond, this bond is ionic, carbon magnesium bond is polar covalent. So magnesium being electropositive, this carbon equals negative. So this carbon with negative is a very strong nucleophile or a very strong base. So this aryl magnesium halide, if this comes in contact with acidic hydrogen, immediately this is destroyed to give you benzene. So we have look at this. When this comes in contact with water, this gives you benzene. When this comes in contact with alcohol, again this forms benzene. So when this comes in contact with acetylenic hydrogen, which is also acidic in nature, so this again gives you. So in presence of protic solvent or acidic hydrogen, these Grignard reagents are destroyed, giving rise to arenes or benzenes. So this reaction is to that of alkyl halides. Alkyl halides react with magnesium to give you Grignard reagent, and this Grignard reagent is stable only in the absence of aqueous medium or dry solvent. So this is the reason why Grignard reagent is to be prepared in dry ethereal condition. Second reaction, that is substitution reaction. As we have discussed earlier, these aryl halides does not undergo normal substitution reaction, that is nucleophilic substitution reaction. The reason being, carbon halogen bond is much stronger due to resonance, double bond character appears, so this becomes stronger bond and cannot be broken easily. Second reason was benzene cation does not form, so SN1 reaction cannot take place due to the steric hindrance of rear side attack. This cannot take place SN2 reaction. So if this does not undergo normal SN1 or SN2, then this must undergo substitution reaction by different mechanism. So when this benzene contains electron withdrawing groups, strongly electron withdrawing groups at ortho and para position, then the rate of nucleophilic substitution reaction increases. Presence of strong electron withdrawal groups at ortho and para position increases the rate of substitution reaction, that is nucleophilic. That means now for this a different mechanism has to be proposed. So look at this. We have look at this halobenzene. Now this reacts with sodium hydroxide. So this does not undergo reaction with sodium hydroxide. But by using this sodium hydroxide, but under vigorous condition, like temperature is 300 degrees centigrade and pressure being 300 atm, so we are having high temperature and high pressure condition. Under this condition, this Cl is replaced by OH. We get this OH. So this is Dawes process. For preparation of phenol from halobenzene. So, but if we have look at this halogen along with this very strong electron withdrawing group at ortho and para position, then this immediately reacts with sodium hydroxide under normal condition. So this gives you OH, NO2, NO2, NO2. Trinitrophenol, which is known as picric acid. Though this is not an acid, but this is known as picric acid, but this is stronger acid than that of benzoic acid due to strong electron withdrawal by 3 nitro groups. But we have looked at this nitro. In the first case, we have 3 electron withdrawing groups as ortho and para. In the second case, we have 2 electron withdrawing groups as ortho and para. Then the rate becomes slower compared to that of this trinitrogen substituted halogen. So this requires reaction with sodium hydroxide followed by heating. Then this gives you substitution. That means as the electron withdrawing group increases, the rate of reaction also increases. So this substitution reaction proceeds through a mechanism known as SNAR, substitution nucleophilic aromatic. Substitution nucleophilic aromatic. And this substitution nucleophilic aromatic proceeds via formation of carbanion. Proceeds via formation of carbanion. So look at this. These carbanion can be stabilized by electron withdrawing groups at ortho and para position. So look at this. Electron withdrawing groups at ortho and para position increases the stability of carbanion. So if the stability of carbanion is increased, the rate of reaction increases. So this was the reason. As the number of electron withdrawing groups increases, the stabilization of carbanion increases, so the rate of reaction becomes faster. So look at the steps of mechanism. We have looked at this. CX, this reacts with nucleophile. So this being electron withdrawing group, this being electron rich group. Benzene also contains electron pi electron. So benzene is also nucleophilic. So electron repulsion takes place. Again look at this. When this nucleophile approaches benzene ring, nucleophile is electron rich. Benzene is also electron rich. When these two electron rich comes in contact with each other, there is strong electronic repulsion. Because of this repulsion, nucleophile will have less tendency to approach benzene ring. If this nucleophile does not approach benzene ring, will there be possibility of substitution reaction? No substitution reaction. So this is again one of the reasons why benzene Halobenzenes does not undergo nucleophilic substitution reaction easily. But look at this. This being electron rich, this has to approach electron deficient carbon. So this pi electron is shifted here. When this is shifted here, this carbon becomes positive and nucleophile attacks here. So we have, look at this, X, and we have this nucleophile, carbon is negative. So this negative carbon is resonance stabilized. In the second step of this reaction, this electron, because benzene will try to regain its lost aromatic character. So in the process, this electron is again transferred between carbon, and this has to push out halogen from the system such that this X is being replaced by nucleophile. So all this depends on the stabilization of this carbanion. This carbanion is stabilized by these electron withdrawing groups at ortho and para position. So I'll just show you how this is being stabilized by electron withdrawing. Take this. So we have, look at this, nitro group at this ortho position. So this nucleophile electron is transferred here, or nucleophile approach this carbon. When this gives you nucleophile X, negative charge here, we have N double bond O. Now look at this part of the molecule, negative sigma pi. So we have a conjugation here. So these can be stabilized by this resonance through the electron withdrawing group. Because of this, there is extra additional resonating structures. Apart from this normal resonating structure, there is some extra resonating structures from this external resonance. Because of this, the stabilization of the carbanion is increased. So this is the reason why we require to have a strong electron withdrawing group at ortho and para. So as the number of such type of electron withdrawing group at ortho para increases, the number of resonating structures increases. As the number of resonating structures increases, the stabilization of carbanion increases. When the stabilization of carbanion increases, the rate of substitution reaction increases. So this is the mechanism for this substitution nucleophilic aromatic substitution reaction process where carbanion, and this carbanion is stabilized by electron withdrawing groups. So we should have electron withdrawing groups. Carbanion. Now for this substitution reaction, as I told you, minus I groups increases the rate of reaction, plus electron releasing group decreases the rate of reaction. But when we compare the reactivity of different halobenzenes, so it is F Cl Br I, the reactivity of this towards this SNR mechanism decreases from fluorine to iodine. This can be simply visualized based on the electron withdrawing character of halogen. Fluorine being the strongest electron withdrawing group, this withdraws electron density from carbon, and this carbon becomes more electrophilic, which can be easily approached by nucleophile. As the electron negativity decreases, electrophilic carbon of benzene ring to which halogen is present decreases. So tendency for nucleophile to approach this carbon is decreased. So simply based on minus IFA, we can explain the reactivity order of different halobenzenes towards substitution, nucleophilic, aromatic. Then we have one of the most important reaction of this halobenzene, that is electrophilic substitution reaction. Next reaction is electrophilic aromatic substitution reaction. Electrophilic aromatic substitution reactions of benzene and substituted benzenes. So we have look at this halogen. This halogen is electron withdrawal by minus IFA, and simultaneously this also shows electron released by resonance. So when this releases electron density by resonance, electron density at ortho and para position is increased, that we have explained while before discussing the chemical properties. Due to resonance, electron density at ortho and para is increased. So normally we say halogen attached to benzene ring, halogen shows electron withdrawing character. So this, because of withdrawing character, this is deactivating group, means the reactivity of halobenzene towards this substitution reaction is always less than the reactivity of benzene. But due to resonance, electron density at ortho and para is increased. So this group, this is ortho para directing group. That means whenever we carried out electrophilic aromatic substitution reaction of halobenzenes, the incoming electrophile will always go through the ortho position or the para position. So take different reactions. Reaction with nitric acid plus sulfuric acid, reaction is known as nitration. We have nitro substituted benzene, that is nitration. So nitro group is introduced at ortho and para. We have reaction with oleum or concentrated sulfuric acid, the reaction is known as sulfonation. We have sulfonic group introduced to ortho plus, will have some para compound, the reaction is known as sulfonation. When this compound is made to react with alkyl halides in presence of catalyst AlCl3, substitution and alkyl group is introduced at ortho and para position. The reaction is known as Friedel-Crafts alkylation. Friedel-Crafts alkylation. When we carry out this reaction with RC double bond O X acyl halide in presence of catalyst, and acyl group is introduced to ortho and para position. This is ortho compound plus we have this. This is known as Friedel-Crafts acylation reaction. So nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation. We can also have halogenation. This reacts with halogen in presence of iron. Again, the second halogen will be introduced to ortho position and para position. This is known as halogenation. So these are the electrophilic aromatic substitution reactions of halobenzenes. So this is electron withdrawing group, but due to electron released by resonance, electron density at ortho and para is increased. So this is known as ortho para directing in nature. But when we compare the reactivity of this halobenzene with reactivity of benzene towards electrophilic aromatic substitution reaction, benzenes are more reactive than halogen substituted benzenes. The reason being, this is electron withdrawal by induction, deactivating group. Electron density is slightly less than that of benzene ring. So these are electrophilic aromatic substitution reactions as given by halogen substituted benzenes. Now, some name reactions that we all have discussed in alkyl halides also. Coming to that name reactions, one is known as Wood-Fittig reaction. So this is a coupling reaction of alkyl halides and aryl halides in presence of sodium to give you alkyl substituted benzene. So we have a reaction of aryl halide and reaction of alkyl halide in presence of sodium metal, that is dry ether, when this gives you alkyl substituted benzene. So this is aryl halide, this is alkyl halide. Coupling reaction of aryl halide and alkyl halide with sodium metal in presence of dry ether, which gives you alkyl substituted benzene. This is known as Wood's reaction. So look at this, we have this chlorobenzene plus this reacts with methyl chloride. When this reacts with sodium, so this gives you methyl substituted benzene. If this reacts with CH3, CH2Cl in presence of sodium dry ether, then gives you ethyl substituted benzene. So this is Wood-Fittig reaction. Then we also have a reaction which is known as Fittig reaction. Fittig reaction is a reaction of 2 moles of aryl halide in presence of sodium dry ether. So reaction of aryl halides with sodium, when this gives you biphenyl. So this is phenyl group, this is phenyl group joined through this carbon-carbon bond. So this reaction is known as Fittig reaction. So Fittig reaction, Wood-Fittig reaction, Wood's reaction. The reagent used for the reaction is sodium in presence of dry ether. The only difference being the reactants. In case of Fittig reaction, we use 2 moles of aryl halide. In case of Wood's reaction, we use 2 moles of alkyl halide. In case of Wood-Fittig reaction, we use a mixture of alkyl and aryl halide. So this is, we can say, on the reaction with metals also, or these are known as named reactions. So this is electrophilic aromatic substitution reaction as given by aryl halides, and we have discussed nucleophilic substitution reaction, which is defined by mechanism known as substitution nucleophilic aromatic, and we have also discussed the conditions required for this reaction. And one more reaction that is usually given by this halogen substitute benzene is substitution via benzene pathway. Via benzene pathway. So we have looked at this. This is halogen substitute benzene. This reacts with potassium amide KNH2. So we have K plus and NH2 minus. NH2 minus is a very strong base in presence of liquid ammonia. So we have very strong base. So these base abstract this hydrogen, and this electron is transferred between carbon, and this leaves the system. So when this gives you a very reactive intermediate which is known as benzene. In benzene, these carbon, both these carbon is sp2 hybridized. That means all carbon atoms of benzene is again sp2 hybridized. This is now in the first step. This is a removal. In the second step, this reacts with NH2 again. Now look at this. NH2 attacks here. This electron is shifted here. When this gives you, this Cl was replaced by NH2, and we have a negative charge. So this reacts with ammonia which is present in the solvent. So these take up at H plus and is further converted into. So we have looked at this. This is also substitution, but this reaction proceeds via formation of a benzene intermediate. So for this requirement is normally this reaction is carried out in presence of potassium amide, yeah, sodium amide, which is a very strong base in presence of liquid ammonia. So this mechanism is also known as elimination followed by addition. In the first step there is elimination of HX, and in the second step there is addition of ammonia. So this reaction is also known as elimination followed by pathway. So this is substitution via benzene intermediate or benzene pathway. So this is some of the important reactions or chemical properties as shown by halogen substituted benzenes, or known as halobenzenes. So with this we comes to the end of this chapter, that is haloalkanes and haloarenes. So there we have discussed different types of reaction pathways and what are the outcome of these reactions by use of different types of reagents, different types of substance like nucleophile, electrophile, etc. So with this we are winding up this chapter, and next video lecture we are going to discuss, or we are going to take out a new chapter. Okay, have a nice day.